Alright, welcome back. Now in this video lesson, we're going to go through this paper. Now the questions here are mainly P4, P5 questions, and if you're watching this will be useful for revising topics like water cycle and heat transfer and state of matter, plant, transport system will all be covered in this paper. Let's get started. Now the table here shows the characteristics of three things, A, B, and C observed over a period of time. A tick indicates that it has a characteristic. So you're going to recognize that this table here, for example, if you look at just A, it says that A needs air, food, and water to survive. So A must be a living thing. A can make its own food. Only plant can make their own food. So A should be a plant. Alright, and plants can't move freely from place to place. B can move, but it cannot make its own food and it doesn't need air, food, and water to survive. So B must not be a living thing. For example, B can be a car. Alright, a car can move from place to place. C is a living thing because it needs air and food and water to survive. It can move freely from place to place, just like us. So A and C, we're looking for which of these are living things. So A and C are living things, and the answer is 2. Now Joseph placed 4 identical blocks of ice, A, B, C, and D, at the same location. Same location here often you can infer some information. Same location means that in this context, because this is about melting, which means the temperature is kept constant for all these 4 blocks of ice. Right? Temperature is the same because they are in the same place. So ice block B was cut into 2 smaller pieces. Ice block A wasn't cut. Ice block C was cut into 4 smaller pieces. Ice block D was cut into many smaller pieces. And these 4 ice blocks were identical before they were cut, before B, C, D were cut. Identical in terms of their mass is the same. So what's the difference with cutting? Right, so the cutting results in the cutting leads to an increase in surface area. So what does that mean? So I just do a small demonstration here. Let's say this represents your large ice block A, okay? And it's not being cut. So if let's say heat were to want to melt this block of ice, right? This is A. So how can heat get to it? Heat can get to it from the top here, from the left, from the right, from the bottom. So heat can heat from the surroundings can be transferred to ice block A in these different directions. But what if the same piece, right, as in same size, is being cut? Let's cut it to see what happens. Let me cut into 4 pieces. They were identical sizes at first. Now they're still identical size, but the difference is now it has more surface area. What do you mean by more surface area? So remember earlier on I said heat here can get to ice block A in different directions, right? But how about for B that has been cut into, let's say this is C, I cut into 4 different smaller pieces. 4 smaller pieces. Now for C, that means that instead of heat just being able to melt ice block A from these 4 directions, 1, 2, 3, 4, now heat can get to it from these parts. So many more surfaces now can receive the heat from the surrounding. Many more surfaces here will be exposed to the heat in the surrounding. So of course between A and the many small blocks of C, which one will melt first? Naturally, this one will melt first because more surfaces are in contact with the surrounding, and therefore more heat can be conducted to these smaller pieces of ice, and then of course it will melt first. So this one cut into many small pieces. This will have the most amount of surface area exposed to the surrounding. This one have the least amount of surface area exposed to the surrounding. So which one will melt completely first? And the answer is D, of course. Okay, answer is number 4. Let's go to the next one now. Now, Elaine here put a plant in a beaker of red colored water as shown below. So water is red in color. The next day, she observed the white flowers turn red. So these flowers turn red. That means that the water inside must have been absorbed through the roots, must have gone up through the water carrying tubes to this flower and that flower. So this tells you, now it's important to look at the words, because words have meaning. So in MCQ, how the person who designed the question will try to test your understanding is to see whether are you careful with the words. If you're not careful with the words, then you get it wrong. For example, I bet some of you would have chosen the stem takes in water for the plant. Alright, let's say I'm not sure, because you know the stem contains the water carrying tubes, and that refers to water carrying tube being used for transporting water, not for taking in. Take in sounds like another way of saying absorb. The stem isn't absorbing water. So let's see what other options. Say I'm not sure, I put a question mark, not sure. Sounds a bit iffy. Let's look at number 2. The roots take in water, okay? Remember, take in means absorb. Roots take in water seems correct. And transport. So you are saying the roots do two things: take in water and transport. This is wrong. This part is wrong. This is correct. This is wrong. Roots do not transport. Roots absorb water only. Water carrying tubes will transport water. So this is how it can be tricky. First part can be correct. Second part can be wrong. So when you're reading options in MCQ, you got to read the entire sentence. Don't just stop at this part. Oh, it's correct. Then you choose this as your answer, when the second half could be wrong. Next one. Water carrying tube transport water. You see, this part sounds correct, right? Water carrying tube transport water. However, if you read on, it says the water is from the roots to the flowers. Hey, this part is also correct, because water carrying tube transport water from the roots. There are also water carrying tubes in the roots. So 3 should be the answer. Let's be double confirmed by checking the last one. The water carrying tubes transport water from... Okay, this one, you see, exactly the same words, right? But the second half is wrong. Where is the water from? From the leaves. The leaves trap light to make food. The leaves will transport food. Leaves don't transport water. So this is wrong. So now we're left with 2 options, right? So first and 3. So this one, remember, takes in means absorb. Stem don't absorb. Stem should be transporting water. Alright, and there's a water carrying tube inside the transport water. So 1 is not a good statement. 3 is the best statement here. And that is what she can conclude. Question 4. Linda placed a plant with 2 white flowers, X and Y, into a beaker. There are 2 flowers, right? X and Y inside a beaker of red colored water. So I color it red. At position A, which is this, she removed both the food and water carrying tubes. So I just wrote down for my understanding. Removed food and water. At position B, I'll remove only food carrying tubes. Now Linda left the setup on the table and observed the flowers 8 hours later. Okay, so what happened? Now, if you look at the options, they just talk about the flowers turning red or remaining white. In other words, this question is only about the water carrying tubes. You can ignore the food carrying tubes. Nothing to do with the food carrying tubes. Because why is it only about the water carrying tubes? You just want to check whether did the water reach flower Y to make flower Y red, did the water reach flower X to make flower X red. That's all they're asking. Okay? We know at position A, the water carrying tubes were cut off. So here is cut. Any water that's absorbed, that is transported up the water carrying tube, can never get past position A. That means that flower A will remain white. They were white color flowers, right? It will remain white. So X must be white. If X is white, it's only either 1 or 3. Then next one, this part here, only food was removed, food carrying tube. So in other words, the water carrying tube remain to transport the water up to the flower to make it red. So flower Y will turn red. Answer is 1. Next one. The diagram shows the water cycle A, B, C, D are the different processes in the water cycle. So this is clearly water, right? So before we do this, let's revise your P4 idea and your P5 idea, change in state and about water cycle. Solid, liquid, gas. Alright, gaseous state. Of course, this is a gas, so gas is what we call them as a gaseous state. The state here is called liquid state. The state here, where it has a fixed shape and fixed volume, cannot compress, is called solid. How do you change from this to this? We must add heat to this, like put a fire underneath or something. So there will be heat gain, and this process is known as melting. And when all the solid has melted, it becomes a liquid. For liquid to become a gas, it also must gain heat. There must be heat gain. Like on a hot day, so water will evaporate faster. And this process is known as evaporation. Now it becomes, let's say, if it's ice, if it's water, then of course it becomes water vapor. How can water vapor turn back into a liquid? Well, it must lose heat. Usually it must touch a cooler surface and then lose heat. So here there will be heat loss. And the process here is known as condensation. And how can liquid become a solid? Like we put liquid on your ice cube tray and put inside of your refrigerator, because you want the ice cube to lose heat. There will be heat loss here. And this process is known as freezing. So this is a quick recap on these different processes and the change in state. Now we talk about this. So A is from clearly a liquid, of course must change to a gas. Remember, liquid to gas is heat gain. So heat gain must have A, right, as part of it. So heat gain, A must be present. Let's look at heat loss. So heat loss will be either, there's no freezing here, you don't see ice, right? So heat loss must be the process of condensation, right? Condensation. So gas to liquid. So from water vapor to this, clouds are actually not gas. Clouds are actually tiny water droplets. Clouds are tiny water droplets. So B here involves a change in state from gas to liquid. So here there will be heat loss. So B is where you have heat loss. That's the answer. And that's a double check. Here is a change in state from liquid to gas. Change in state. Here is a process where the gas changed state into the liquid. So answer is 1 for this question. Question 6. The diagram shows how food and water are transported in a plant. Now here, there are two ways to do this very easily if you are confused by all these lines. So let's say I do the first way, which is, let's say I'm very familiar with roots, because I know that roots absorb water, right? Roots absorb water. So I must then start off with the roots. How do I know where the roots are? I see where the water is coming from. So I know the dark arrow here, the bow arrow, is the water. So I look for the bow arrow. Okay, it's moving here, here. So where this starts from? Not here, it reaches here. Not here, the arrow reaches this point. So it starts from W, right? Water is moving from W. This tells me W must be the roots. Then the other way is you can look at the food. So which part of the plant makes food? That will be the leaves. So I look for the arrows, the dotted line arrow, the dashed arrows. Look here and look for where it comes from. I see the dash arrow here, moving to this part, and this is a starting point, right? It starts from here and branches out to these two directions, in these two directions. So that tells me Y must be the leaves. It makes food that is transported in the food carrying tube to all the rest of the plant. So let's see if this is enough to get me the answer. So Y will be leaves. Hey, got the answer already. Let's double check. So W should be the roots. W is the roots. Yeah. That's it. Answer 3. Next one, let's look at number 7. Now, Donald heated some water in a beaker until it boiled. He continued boiling the water for some time. So there was some water in the beaker at about room temperature. Then he boiled the water, gain temperature, right? Increase until it reaches at 100 degrees Celsius. At this point, you have boiling happening. So E to F is boiling. The question says, right, he continued to boil the water for some time. Okay, so here is a boiling for some time. Then it's left to cool on the table. So cooling means temperature start to drop. So he recorded the changes in this graph. Now, is there heat gain here? Of course, here there is heat gain. Is the water gaining heat here? Of course, it is being boiled, right? There's heat source underneath, like fire or your induction cooker or something. So here there's also heat gain. So when the question says heat was gained during EF, that's true. Now, notice, remember I said words are important. The question didn't say heat was only gained during EF. No, it just said heat was gained during EF. That is true. If that's true, means the answer can be either 1, 2, or 4. Now I see B here is important. Let me try to see if B is correct. Water exists in 2 states during EF. EF means boiling, right? So boiling means you have some water inside, you have your heat source beneath, and then it changes into steam. So this will be in the liquid state, here will be in the gaseous state. So long as boiling is happening and there's water to boil, there will be water here in the liquid state, there will be gas here in the gaseous state. And water vapor at 100 degrees Celsius is known as gas, known as steam. So here is true, water exists in 2 states in EF. Then here, the very important helpful word the teachers will give you is the word only. Whenever I see this word, to me, most of the time, this statement is wrong. It's just like if you say, oh, durian is the only food I eat. That's not true, right? You will eat other things. Or ice kacang is the only dessert I eat. That's not true, right? You eat other things. So it says here, of course, sometimes it could be true, but in this case here, and in many cases, only tells you you have to pay special attention. When it says evaporation took place only during FG, which is here, that's not true, because evaporation takes place at any temperature. So evaporation is taking place here as well, but here is actually called boiling. Evaporation is also taking place here. Even if you don't add heat to it on a fire, with a flame, water on your table is also evaporating. Water on the floor is also evaporating. So this is false. If C is false, I know this is wrong. If B is true, I know this is correct. So answer is 2. Question 8. Kumar poured the same amount of water into 3 different containers, A, B, C, as shown here. And they were placed in the same location. Remember in the beginning we talked about location? location is for you to infer some important information. What information? Same location under the sun, right? Same location means the temperature is the same for all the water in these 3 containers. It means the wind condition is the same. If it's windy, the wind will blow over all 3 containers. If it's hot here under the sun, it is the same degree of hotness for all these 3 containers. Same. And we talked about rate of evaporation earlier on. And remember the acronym WET. So W stands for wind condition. T stands for temperature. So since these 2 will be the same for all 3 of them in the same location, these 2 will not be the factors that determine which of these evaporate first. It is E. And what is E? E stands for exposed surface area. This has a smaller exposed surface area. The water can only evaporate through this tiny space here. Here, much bigger exposed surface areas, 10 cm across. This one is the biggest. Alright, a lot more surface area for water to evaporate. So if you have put water in these 3 containers, same amount of water, the water in container C will evaporate the fastest. So after some time, I can check this graph. I will know that C must have the least amount of water. So this is the one that shows C at the very bottom, right? Amount of water left, C is right at the bottom. This 2 has A here, wrong. Bottom here is A, wrong. Which one will have the most amount of water? The one with the smallest surface area. So A should have the most amount of water left after 1 hour. Most amount is on top. You see? Amount of water, most. This is wrong. So answer is 1. Now, if you are a P6 student watching this, you can hear the explanation. If you are a P5 student, you can just forward and skip this. Basically, this is quite a simple question for the P6s. What affects the rate of evaporation? One thing will be the light intensity. The lamp is the same kind of lamp. And the distance here will affect the light intensity. So to the plant here, this plant is receiving a certain amount of light. When you pull the lamp further away, see 60 cm away, now the light intensity drops. So here is much dimmer compared to this part. So the rate of evaporation here will be lower. Here the rate of evaporation will be higher. If the rate of evaporation is, rate of photosynthesis, what am I saying? So the rate of photosynthesis here will be lower. The rate of photosynthesis here will be higher. So the rate of photosynthesis is higher, there will be more oxygen bubbles here. If the rate of photosynthesis is lower because of the lower light intensity, there will be fewer oxygen bubbles. So I expect to see a graph, right? In terms of oxygen, A should have more, B should have less. So I'm looking for a bar graph like this. And the only one that looks like this is here. So answer is 4. Question 10. Now this is about your, again, change in state. We talked about this many times, so we're going to move a bit faster here. So this state P here, liquid to solid, is called melting. So melting. Then liquid to gas is called evaporation. Liquid evaporation. Okay? Answer is 1. Sorry, I made a mistake. Liquid to solid, so sorry about this. Liquid to solid means it's losing heat, so it is called freezing. Okay, liquid freezes into a solid. Here liquid evaporates into a gas. So P should be freezing. Okay, even teachers make mistake, right? So we got to always double check and reread the question when we check. Then this part is evaporation. So answer is 3. Next one, the diagram shows, now this is the first time we're encountering human circulatory system in this paper. So I'll take a bit of time to explain it. And I'll show you again the simple way of doing it. It shows the direction of blood flow in a human body. So where does it flow from? We talk about the rich in oxygen, okay? So blood that is rich in oxygen comes from a particular organ. It comes from the lungs. So just like how we did the water traveling in the, last time we did a question like this one, we're going to use the same method to do this. So let's find the lungs. So I find the rich in oxygen blood first. And this will be this arrow and this arrow. And it's moving in this direction. So this tells me where is it starting from, the part where the blood is rich in oxygen, from here. And therefore this must be the lungs. Because the lungs is where we breathe in air through the nose, go down the windpipe into the lungs, then the oxygen get absorbed into our blood inside the lungs, get sent to the heart, that is then pumping the oxygen-rich blood to the rest of the body. Then the body will send the blood that is poor in oxygen and rich in carbon dioxide to the heart to be pumped over to lungs to get rid of the waste gas carbon dioxide. So now very clear, T must be your heart and U must be your lungs. Okay, answer is 3. Now let's go to question 12. Now question 12 here, this is a good question, as in this question, right, please master it. I see it almost every year in PSLE MCQ section, almost every year, almost. You can check if you don't believe me. So if you know how to do this, you guarantee your 2 marks. The statements below describe substance R at different temperatures. So at 35 degrees, it has a definite shape and volume. At 85 degrees Celsius, it does not have a definite shape, but has a definite volume. At 128 degrees Celsius, it can be compressed. Let's do a quick revision about the states of matter and their characteristic. Which one have a definite shape? Only solid have definite shape. Which one has definite volume? Only solid and liquid has definite volume. Which of these can be compressed? Only gas can be compressed. Okay? Now let's take a look at this is how I'll do my model for doing this. So at 128 degrees Celsius, it can be compressed, which means it is a gas at this temperature. So anything above here, above 128, it is a gas. At 35 degrees Celsius, it has a definite volume and shape. Definite volume and shape, it means it's a solid. So at 35, which means at this temperature, anything below this, it must be a solid. At 85 degrees, it does not have a definite shape, but a definite volume. So 85 degrees Celsius, no definite shape, but definite volume, so it's a liquid. So here it is a liquid. Alright, now let's see, what could be the possible melting point and boiling point of substance R? Melting point is the temperature where a solid melts into a liquid. Boiling point is a temperature where a liquid boils into a gas. So let's check melting point first. 5 degrees is below 35. Cannot be the melting point because at 35 is still a solid. So any number smaller than 35 must be wrong. So wrong, wrong. Left these 2. Let's check boiling point now. So ignore these 2 already, right? Boiling point means that a temperature must be underneath 128 or at 128. Because let's say if 110 is the boiling point, so it's liquid up to this point, liquid here. So once it hit this, start to boil and turn into a gas. Yeah, it's possible, gas. So this is a possible answer. 130 cannot be. If you say 130 is a boiling point, means at 130, below this part, it is still a liquid. But we know from this statement, at 128, it can be compressed. And liquid cannot be compressed. So answer is 3. Now we go on to booklet B. If you like, you can take a break now, a 5-10 minutes break, and then we come back to the video. Alright, let's continue. Now, Sam filled 3 identical containers, A, B, C, with 200 ml of water. He placed a plant in container B, another similar plant in container C, but he chopped off some of the roots. Each container was tightly covered with a lid. Alright, and the purpose of the lid is like a layer of oil. same idea, which is to prevent evaporation of the water from the container out of the container. Yes, water can evaporate, but it will condense here and will drip back. So water is still like trapped inside the container, unless it has a way out, like through the roots, up the stem, to the leaves. So what was Sam trying to find out? Well, obviously he's trying to find out whether the number of the roots will affect the amount of water absorbed. Now, if you write the length of the roots, I suppose it's possible, but I think the better answer is still the number of roots. I say why length is possible because here he cut off, you see, so it's shorter now, where here was longer. Okay, but I think this is the better answer, number of roots. What happens to the water when it reaches the leaves? When it reaches the leaves, it will go to the stomata. Stomata is an opening on mostly the underside of the leaf. When the water reaches the stomata, the water will evaporate. Simple answer, it will evaporate. Now, since we know this, before we turn, let's take a look at this again. So, which of these do you think will more water leave the container? In other words, which of these will there be the least amount of water after some time? Must be this, right? Because more roots absorb more water to be transported to the water carrying tubes to the leaves and then escape through evaporation. So B should have the least amount of water left. Which one would there be no change in amount of water? Of course A, right? Because there's no plant inside, there's no roots absorbing water. So the water inside here remains inside here. So this one, A, the water remains unchanged. Now we see what it looks like on the graph. So if the amount of water remains unchanged over some time, you see, it's horizontal, no change, same amount. The least one is this, it goes right to the bottom, right? Least amount of water, the very low number. So that's what we do here to answer part C. Now question D, repeated the experiment without covering the container. Remember, the container is to prevent the water from evaporating out of the container. So what happens, he realized that when he did it without the lid, all the containers here, all the water was left. It means when he did it again, even for container A, right, with no plant, there was still a decrease. Everyone had decreased, but even this one showed decrease. So what's the answer? Well, water in the containers evaporated into water vapor and escaped into the environment. Why is this last bit important, escaping into the environment? Because even without the lid, water can still evaporate, right? You can see there's some gap here. But this evaporated water, the water vapor will still be trapped inside. Without the lid, the water vapor can escape into the environment. That's why I added this part here, and escape into the environment. Okay, hanging there, we're finishing. 2 more questions. The table shows the boiling and melting points of 3 substances P, Q, and R. So melting means solid change to liquid. Boiling means liquid changes into a gas. Now this question, I'm going to show you how to use the table like this to pen down your annotation easily. So, but if these are the melting point, right? If 50 is the melting point for substance P, that means this part here should be the solid. At 40 degrees Celsius, at 30 degrees Celsius, at 10 degrees Celsius, is all solid. Then it also means that this part here, between 50 and 300, it must be a solid. And beyond this, because it's boiling point, sorry, it's not solid, I wrote wrongly, it's a liquid, liquid. Solid is here, this is the solid. On this side of the melting point is a solid. In between melting and boiling point is your liquid. And this side here, of course, will be your gas. So when you think like this, all this temperature on this side here will be solid. All the temperatures on this side here would mean that this substance have turned into a gas. and anything in between here means the substance is in the liquid state. So at 25 degrees Celsius, where's 25? For substance P, 25 is in front here. So for substance P, it is a solid state. Simple, right? Let's find out where is 25. For substance Q, Q is this. Where is 25 for substance Q? 25 is here, between 0 and 100. So for substance Q, it is in the liquid state. What's the difference between boiling and evaporation? Now, although you're not really required to memorize stuff, but there are questions every year in the open ended section that ask students to state certain definition. So this is one of those questions that happened before. So what's the difference between boiling and evaporation of water? So boiling happens at just one specific temperature, whereas evaporation happens at any temperature. So that's the difference between these two. After washing his hair, this Mr. Press, very stylo, uses a hairdryer to dry his hair. The hairdryer blows hot air at his wet hair. So you see the clue here, hot air, and it is a moving air, so it's wind. Remember our WET, factors the effect rate of evaporation. So here is blowing air towards his hair, right? So there is wind. Since it's hot, there's higher temperature. So these are the two factors you have to mention in your answer. So the heat, which is a higher temperature from this, and the wind, these two helps him to dry his hair faster. How? These two factors, heat and wind, increases the rate of evaporation of the water on his hair. Now, the wife dries her hair differently. Yeah? So she uses a comb to spread out her hair. Okay? How does this action of spreading her hair helps? Well, spreading her hair is to increase the exposed surface area of the wet hair, and that will increase the rate of evaporation. So that's the action here. Okay, last question now. Good job for hanging in here. Kenneth cut an apple into slices and put them into a beaker. These are the apples. He covered the beaker with a plastic cling wrap. This will be your cooler surface. And put it over a flame. After a few minutes, he observed substance F forming on the insides of the plastic cling wrap. There's no water here. So how can there be evaporation? Can. Fruits are juicy, right? So F would be water droplets. How did it get there? The water in the apple, or moisture, you may use the word moisture. The water in the apple gained heat from the flame, see? And then the water evaporated into water vapor. That's part one of your answer. Water vapor is inside now. How did water vapor change state to become liquid? Well, the water vapor touched the cooler surface of the cling wrap, lose heat, and condense into water droplets. That's the second part of the answer. Alright, now for the last part. Mrs. Lin prepared crispy peanut cakes for her son Kenneth to bring to school. After cooking, she placed the hot pancakes into a box with holes at the lids. Now the holes will let water vapor inside escape. Now this is naturally very moist. So when it's hot, the heat from the pancake will cause the water in the moist pancake to evaporate. If you're going to eat Mr. Bean kind of pancake before, you know what I mean. So how do the holes help to prevent the crispy pancake from becoming soggy? Soggy means it no longer is crispy. It becomes wet. How did it become wet? Well, let's try to understand. So the warm water vapor that's in the box can escape through these holes. So less water vapor would condense on the lid of the box. When it condenses there, they will drip down on the pancakes. Since there are going to be less water vapor, there will be fewer water droplets to drip down on the pancakes. Alright, good job for hanging there for this 40 minutes lesson. This haven't covered all the topics that you will need. So example, your plant reproduction, human reproduction, the fish circulatory system wasn't mentioned in this paper, but at least this covers a lot on sections that you were not too sure of, which is basically the water cycle part, which I think many of you have forgotten, my dearest 5 CARE student, okay? So do use it to revise. Alright, I'll see you in the next video. Take care. Goodbye.